Hello and welcome. Hi, my name is Lucinda Offer. I'm the Education and Outreach Officer here at the Royal Astronomical Society. And we're here today because the Hubble Space Telescope launched this month, 35 years ago in 1990. The Hubble Space Telescope observes ultraviolet, visible, and near infrared light. And you're going to hear more about that from our speaker today. The Hubble imaged everything from planets in our solar system to galaxies billions of light years away. It has made way for the James Webb Space Telescope and an upcoming Nancy Grace Roman Space Telescope called Roman, which is not an acronym because NASA likes a lot of acronyms. Roman is just for this woman's name. Her name is Nancy Roman. It's a name worthy of remembrance because she is also known as the mother of Hubble, and she was NASA's first chief of astronomy and championed the Hubble Space Telescope when she was there in the 1960s. She was pivotal in establishing NASA's space-based astronomical observatories program. And in that vein, we have Dr. Beasor with us today from Liverpool, John Moores University. She's currently a Royal Society Dorothy Hodgkin Fellow and academic staff member at the Astrophysics Research Institute at LJMU. She obtained her PhD there in 2019 and was awarded a prestigious NASA Hubble Fellowship to continue her research at the National Optical Infrared Astronomy Research Laboratory, NORLAB, in Arizona. An expert on the lives and deaths of massive stars, her research focuses particularly on the behavior of stars leading up to supernovae, including how their stellar winds or nearby companions may alter their final fate. Please welcome Dr. Beasor.
Okay, hi everyone. I'm really pleased to be here talking to you all. You've got, the privilege of getting the second run of this, so all issues have been ironed out, so no technical issues in this talk, hopefully. But yeah, so I'm going to be talking about the Hubble Space Telescope in relation to my field of research, which is massive stars. So Hubble has been up in space observing for 35 years as of April 24th this month. And it's been doing an absolutely outstanding job. Every astronomer in the world uses data from it at some point, I would say. It's hugely useful, and it's been used across every single field of astronomy. But the idea to put a telescope in space came about in the 40s. It was suggested by this guy, Lyman Spitzer, who wrote a paper in 1946 about the possibility of having an extraterrestrial observatory rather than just using ground-based observatories, as is still the norm, really. And then in the figure up on the left, you can see a kind of artist rendition from the time of what they thought this space observatory might look like. And if we look at Hubble today, you can see it does actually kind of look like that picture. So Hubble is a telescope that is a few hundred miles above the Earth's atmosphere, and there are a few advantages to put in a telescope in space like this. So one of the first ones is we live in a world which is filled with lights from our houses, from cars, from everything. Basically, cities glow, and this glow of a city or a house can kind of cause the stars in the sky to appear fainter, so it's harder to see them. You may notice if you go on holiday somewhere in rural Wales, you can see a lot more of the sky than you might see in central London. And if you go observing at some of the dark sky sites around the world, for example, mountains in Chile or Hawaii, you can get a much better view of the Milky Way. You can see it with your eyes without any need for cameras, and it's really outstanding. But to get telescopes to these dark sky zones, you have to basically bulldoze the top of a mountain to do it. So it's quite tricky. There's not that many good dark sky zones in the world. But if you put a telescope in space, then you can avoid this kind of light pollution issue because you're way above anything that's emitting light anyway. So that is one reason for putting a telescope in space. Another is that Earth's atmosphere can really get in the way of observations. So one way is that there's a lot of, for example, turbulence in the atmosphere. There's a lot of there can be a lot of dust. There can be a lot of, well, we call it astronomical seeing. So basically, the atmosphere can cause images to appear more blurry than they do when you go above the Earth's atmosphere. So in these figures here on the left, we have an image of Pluto and its moon Charon. In the ground-based image on the left, you can see it kind of just looks like a little blurry shape. You can't really see that there are two distinct objects there. But when you look with HST, which is the Hubble Space Telescope, you can see very clearly that there is Pluto and there is another object around it. And we see it again with this galaxy on the right. So in the left-hand image, which is the ground-based image, kind of just looks like a bit of a smudge, bit of a blur. It's hard to see if that object on the left is a star or a galaxy or what it actually is. But when you take an image with Hubble, all of a sudden you have this vastly increased resolution. And now you can see the spirals even in that little yellow blob on the left, and you can see loads more features in the galaxy on the right. So we get much better resolution when we move our observatories to space. So you can see that again in this galaxy here. So this is NGC 3370. So the left-hand image was an image taken from the ground in 1994. And the image on the right is a Hubble Space Telescope image taken in 2003. And you can see the amount of detail is just hugely different to the image on the left. You can see that these little kind of colorful spots around the galaxy aren't just stars, they're not just foreground objects. A lot of them are actually galaxies in their own right, at different orientations, different kind of shapes. So there's a whole load more information that we can get with this higher resolution. Another reason is that we can access areas of the electromagnetic spectrum that we can't access from the ground. So Earth's atmosphere is really good at protecting us from the sun, but it also blocks a lot of light that we find interesting for looking at astronomical objects with. So for example, in the infrared, the Earth's atmosphere has a lot of water in it, and the water can absorb some light and make it difficult to see things at certain wavelengths. Also with ultraviolet, again, we want the atmosphere in the way to protect us from the sun, but it blocks out a lot of information. Ultraviolet light can trace very high energy phenomenon that we just cannot see from the ground. And again, even certain wavelengths of optical light can be blocked out by the atmosphere. So we just avoid losing any of these wavelengths if we move the observatory to above the Earth's atmosphere. So there's a strong case for putting a telescope in space, despite the logistical difficulties that it kind of poses. But in 1990, after a lot of planning and a lot of attempts, the Hubble Space Telescope was put into orbit on board the NASA Discovery shuttle. So there it is on the left on its way and traveling. As of April 25th, it has been deployed into space. And it's in this low Earth orbit, as I mentioned, so it is a few hundred miles above the Earth's atmosphere. And that was a very good spot for it because it was actually serviceable by astronauts going aboard Discovery. And that here's an image of an astronaut doing service work on the Hubble after it had gone up in 1990. And this is actually a very good thing because when it first went up, the images weren't super impressive. The image on the left was the first light image, so the first publicly released image taken with Hubble, and you can see it's super blurry. So you can imagine how disappointed everyone was after they put this really expensive telescope in space and the image came back really blurry. And the issue was a problem with the shaping of the mirror. The light wasn't focusing as it was expected to, but luckily they were able to send up some astronauts to put a new lens in the way. So basically giving it its own pair of glasses, and you get much sharper images now. So the issue could be fixed just by sending up some service, doing some service missions. And there were 5 missions following the launch of Hubble. So each servicing mission, different instruments were added, instruments were tweaked, things were upgraded, things were taken off. So it's been really useful having a telescope in space that has been able to be adapted with different instruments throughout the years. And this carried on until the retirement of the Discovery shuttle in 2010, I think it was. So it's a really unique observatory for this reason. So just a few little facts about Hubble over the years. So the Hubble Space Telescope has taken over 1.7 million observations throughout its lifetime. And that is over 100 million astronomical objects which have had data collected for. And that sounds like a lot, but actually it's only 0.1% of the sky. So the sky is actually far bigger than you can even like really get your head around. So it's done a lot, but still somehow hasn't covered the entire sky, which is kind of crazy. And it's observed light from objects that are at the furthest reach of the universe, so 13.4 billion light years away, right near to as close to the Big Bang as you can get with visible light. So it's clearly an impressive telescope, and I'm now going to show you how Hubble helps my field, the field of massive stars and supernovae. So I'm going to talk about what Hubble sees when we're talking about massive stars. So I'll begin by just making sure everyone is up to speed and talk about what a star actually is. So a star is a hot ball of gas, so it fuses hydrogen to helium in its core for most of its life. The most famous example, of course, is our sun. But I look at massive stars, and these are stars which are at least 8 times as massive as our sun. They can be up to 200 times as massive, or sometimes even bigger, depending on the papers that you read. And because they're so much more massive, they live very short, fast lives. So they age much quicker than a star like our sun. And for this reason, they're far rarer. So only 1% of all the stars in the sky are massive. Just lower mass stars are far more complicated, far more common. So they're a really interesting, unique system of objects to look at. But we're going to be going through how you form these stars and what their lives kind of look like, because it is a little different to us than to a star like our sun. So we'll start at the beginning. But actually a good place to start when looking at massive stars is just to look at the Orion Nebula. And the reason is that there's actually a lot of massive stars or star-forming regions in here that are relevant to this topic. So if you look at Orion's belt, these 3 stars are all blue supergiants, so these are all also massive stars. We also have Orion's shoulder up here, this kind of red star, that's Betelgeuse, our nearest red supergiant neighbor. And then down here, if you look at the sword, this is Orion's sword here, you can see kind of like a pink blurry patch in the middle. And if we zoom in on that, this is a Hubble or HST image of the Orion Nebula. So this is basically a star-forming nebula. So it's like a stellar nursery. So it's one of the nearest massive star-forming regions to us. And within this region, a lot of new stars are being born by dust collapsing. But I will tell you more about that in the next couple of slides. So here it is again, the Orion Nebula. So this is an image from the Hubble telescope. So you might see me refer to it as HST. But it's been taken across multiple filters. So when you look at an object like one of these nebulae with just optical light, just like what you see with your eyes, it can look quite different to what you're seeing when you look with multiple wavelengths. So these colorful images are generally actually multiple images stacked together. So just to show you again, this is a different nebulae. This is the Lagoon Nebula. And at first we're looking at it in visual light, so you can see lots of dust. And if you look now in infrared, you can see that the dust kind of fades away and you can see the stars behind it. So when you see if I'll do that again, it's kind of quick. So as you move to the infrared, you start to see through the dust and reveal stars behind this kind of dusty plume that you just cannot see with optical light. So it's really useful to have a range of wavelengths when you look at the sky. Okay, but these nebulae, while they're really pretty, they don't just sit there. They have their own gravitational pull, and eventually this kind of lump of material starts to collapse in on itself. So the structure in the clumps will have their own gravitational pull, and it all begins to collapse, and gravity clings to any area that is kind of knotty. So it kind of like the areas that are more dense will pull more stuff in, and you end up with a collapsing cloud and material building up around these clumps. Okay, so this is a simulation of that. So this is a star-forming nebula, very spherical one. They're never that spherical. But this is it at 0 years, and this is it evolving over the next few million years. So you can see as the cloud collapses, there's kind of more yellow regions or the denser regions, and you can see it starts to collapse and form these kind of filamenty or knotty type structures. And it's in these kind of denser regions that the stars are being ignited, the stars are forming. The little dots flying off, I think, are just representing energy. Those aren't stars, but basically anywhere you see the really yellow regions is an area of high star formation. And so in this case, it was a massive cluster that was only about 6.6 million years. But eventually these star-forming regions form regions that can eventually form a protostar. So it's not quite a star yet, but we're on our way. So it's called a protostar. So this on the left is an artist's rendition of what a protostar might look like. So it's material that begins to spin and collapse, and it'll throw off jets as it is spinning. So on the right, we have another simulation of what this kind of looks like. So the material is collapsing and it's getting denser and denser and denser in the middle, and it's throwing off these kind of big jets, magnetic jets of energy. But it's still not quite a star because there is no hydrogen burning in the core. And I'm showing you these nice images and nice simulations because the data in reality is not super pretty. So that object in the middle, that kind of little blobby bit, is a protostar, but you can see the jets there indicated by the purple arrows. And again, another protostar here. It's just very dusty, a very difficult object to kind of decipher. But not all of this, the material in those star-forming nebulae will go on to form protostars. Some of it will just hang about in the interstellar medium. Some of it will form asteroids. Some of it will form planets. But a lot of it will go into stellar masses. But at some point, the ignition in the stars does turn on, so they do begin getting hot enough to fuse hydrogen. And at that point, we finally have a proper star. So we move on to the main sequence. Okay, so this figure is called a Hertzsprung-Russell diagram, and basically it's how astronomers like to figure out what kind of star we're looking at. So you basically take a star, whichever one you're looking at, and you put it on this figure that shows temperature versus brightness. So the type of stars that I'm interested in are red supergiants. So they're really cool. They're over on the right-hand side of the diagram, and they're way at the top because they're some of the brightest objects in the sky. But stars will spend most of their lives on this kind of path in the middle. It's called the main sequence. So they will spend most of their lives here before moving off and going to their various endpoints. But the main sequence is where a star is burning that hydrogen and fusing it into helium. So for a star like our sun, it can spend billions of years there. So our sun is about 5 billion years old, and it's probably got about another 5 billion years to go. Whereas a massive star, so one about 8 solar masses, is probably only going to live on the main sequence for a few million years, which is not very long in astronomical terms, and especially because these objects are very rare. So when you compare it to the lifetime of a star like our sun, it's really just a flash in the pan. But it's difficult to see stars in the main sequence at first because they formed in these very, very dusty regions. So to be able to see them, you need to wait for that dust to kind of clear out. And luckily, when stars are very massive, they have very strong winds. And these kind of winds, it's called feedback into the kind of region, kind of blows out a lot of material. So here is a little simulation showing that. So it's a cluster in the middle, and these winds are like forcing out a lot of the dust. So you can begin to see what is actually going on once the dust of the nebula has cleared away. So it's quite dramatic there, but you can see it kind of leaves some dust around, but there's very clear like cavities where you can now see, what's underneath. And this is an example, another Hubble image of one of these stars, which has a very powerful wind. So this is a Wolf Rayet type star. So these are very massive hydrogen poor stars. And they have winds that can reach velocities of up to 90,000 miles per hour. So they're very, very powerful. And in a young cluster, you might have tens of them that can like really blow a hole in all of this dust. So that's the star right in the middle. And then all of the kind of red, orangey stuff around it is kind of outflow from the wind. It's dust that's been picked up by the wind. So it's really blowing a hole in its cluster. This is obviously a zoom in. But when you look at star clusters, you can see that they've evacuated a lot of dust. So in the left-hand image, we have NGC 3603, and you can see the star cluster in the middle, and you can see how the dust has like been blown out of the way by all of these stellar winds. And another very beautiful looking nebula is the Pillars of Creation, or the Eagle Nebula. And again, you can see that these plumes have been kind of formed by stars blowing dust out of the way, making these really kind of funky, dramatic shapes. But this is a young star forming region, and there are a lot of young stars growing in there, hence the name Pillars of Creation. So if we want to study stars on the main sequence, we need to find a lot of them, and we need to look for what are called super star clusters. So this is M83, otherwise known as the Southern Pinwheel Galaxy. So if we zoom in on it, so this is a Hubble image, this is a different Hubble image of a specific region. If we zoom in here, each of these little circled areas is a superstar cluster within this galaxy. And these superstar clusters can contain anywhere between around 1,000 times the mass of our sun up to around 100,000 times the mass of our sun in a relatively small kind of area. But these have a lot of massive stars in, depending on the size of the cluster. You could have a few hundred, might have 10 or so. But we need to be looking for these superstar clusters in order to study how these massive stars spend their time on the main sequence. It's easiest to observe these kind of superstar clusters by looking outside of the Milky Way as well. And that's because a lot of superstar clusters lie in the plane of the Milky Way. So Milky Way is a spiral or disky type galaxy, and we also lie in the plane. So to try and observe clusters within the plane, it's almost like you're trying to look at a patterned china plate by just holding it up and looking at it flat on. So it's really difficult to kind of figure out what's going on directly in our eye line. And in addition, dust makes things very complicated. So dust has a major impact on astronomical observations and can really disrupt what we see. So just to show you that visually, stars emit light across the electromagnetic spectrum. So this star, for example, is kind of yellowy, so it peaks in the kind of yellow region of the electromagnetic spectrum, and there's no dust in the way, so we see it as a yellow star. But if you stuck a blob of dust in the way, this dust cloud will absorb light and it will re-emit it at redder wavelengths. So basically it deflects light, and what you're looking at, even though it's yellow, will appear more red to you. And that's just because there's dust in the way. And you can see this effect when you look at clusters. So the cluster on the left is an external cluster, so it's not in our Milky Way, and it's not very dust extinguished. So all of the stars there look very blue and bright. But when we look at a cluster that's a similar-ish age to the one on the left, but it's in the Milky Way's plane, you can see how much redder these objects look, even though they're actually very similar to the ones on the left. So the dust is making the stars appear far redder. It also makes them appear fainter at certain wavelengths. So it's easiest to observe these superstar clusters when we look outside of our Milky Way. If there's a very extreme amount of dust, you might not see anything at all. So, for example, if you look in the Milky Way, you can see these regions that just look completely blacked out, these kind of dust lanes where it looks like there's no light at all. That's because there's so much dust that it just completely blocks any light and won't let any escape. It's kind of scattered it all too much. So that's what those dust lanes are. So once we found stars in a superstar cluster, we can study them, and then these stars eventually will move off the main sequence, and in the 8 and above solar mass range, will move on to become red supergiants. So these are the kind of stars that I primarily work on. So they're the best. That's just a professional opinion. But these are the stars that most massive stars will become before they end their lives. Okay. So on the main sequence, stars are fusing hydrogen into helium in their core, and this is a reaction that occurs until the star depletes itself of its hydrogen fuel. And at that point, it begins to burn helium in its core. And this is a reaction that kind of releases more energy, and the star needs to put that energy somewhere. So what it does is it swells up and cools to kind of dissipate some of this extra energy to keep the star stable. So a star like our sun will swell up to become a red giant, so not a red supergiant, and this is it to scale in the bottom right down here. So you can see that that's our sun. This is it to scale with a red giant star. So pretty dramatic difference. So here's another way of showing that. The sun and a red giant kind of to scale. But the type of stars I look at are red supergiants, and here it is kind of to scale. So it's quite different. They are quite a bit more expanded, more luminous. They're cooler. Their radii are far bigger than the sun or than red giants. They're the brightest things in the sky because they are so expanded. And just here's another way to show that kind of scale. So this is a famous red supergiant, VY Canis Majoris, just a cartoon image of it. And then there is the sun to scale on the left. So in the left-hand image, you can just about see it, a little dot, but in the main image, you can't see it at all. And then we've also highlighted Earth's orbit in this as well. So you can see that a red supergiant is far more expanded than even the Earth's orbit. And to scale with our own solar system, so this is our solar system to scale. So you can see the Earth's orbit very much in the middle in the green line there, and we've got Jupiter, Saturn. So a red supergiant, if it was plonked in the middle of our solar system, would be more expanded than the radius of Saturn. And you can see there the red supergiant has an angry face, and that's because stars aren't super smooth, chill things like you see in these kind of cartoons and nice images. There's a lot more going on the surface. So if we look at a star like our sun, you can see very clear convective cells on the surface of it. So these are just kind of like a pot boiling. It's just regions that are moving energy to the surface of the star. So this is, I think this is a real image, but I can't remember what telescope it's from. But there's these tight little convective cells, and they move around, and you get sunspots, you get areas that are more active than others, but they're very, very fine across the surface of the sun. If you look at the surface of a red supergiant, if we could, it would look something more like this. So they have these huge convective cells that can be as big as the radius of the star. So they're absolutely huge convective cells moving vast amounts of energy to the surface of the star. So it's not super smooth and calm. It's actually transporting a lot of energy in kind of a crazy way. So this is a simulation of what the surface of a red supergiant might look like. But actually, when we look at nearby red supergiants, we don't see any of this because these stars are actually very, very dusty a lot of the time. So this is the star that I mentioned before, VY Canis Majoris. So this is that very expanded red supergiant, and this is it imaged in 3 different wavelengths with the Hubble telescope. And you can see it doesn't really look like what you might expect a star to look like. So it's really dusty. It's really asymmetric. There's a lot of material around it. So it's because these stars have quite strong winds that can pick up material and throw it out into the universe. They have mass loss rates that go on throughout the entirety of the red supergiant phase. So it doesn't really look like what you might expect a star to look like. And we get such a good image of this one because it is pretty nearby. This one is in the Milky Way. Usually we just see these red supergiants as little dots, but this one, you can just see how crazy it is because it is so close. As I mentioned before, our nearest red supergiant is Betelgeuse, so that's it up there in Orion's shoulder. So this one is less crazy than that VYCMA. It's kind of got a more normal mass loss rate. So it doesn't look quite as wild as that yet, we don't think. But who knows what will happen with that one. Okay, so a star may spend about 1 million years as a red supergiant, but it is the kind of final main phase before a star is going to end its life as a supernova. But before that happens, it gets extremely unstable, and a star may have explosive outbursts prior to ending its life. So this is an image of a luminous blue variable called Eta Carina. So this is a nearby system. So it is, or it was, a star system that in the 1840s had this kind of crazy outburst. It was called the Great Eruption, and it became one of the brightest stars in the night sky, just looking up with your naked eye. So in one day, it ejected around 10 times the mass of our sun. And so it ejected it in a highly asymmetric way. You can see all of these outflows here. So again, this is Hubble imaging of Eta Carina. And it's thought that actually this was a triple star system. So maybe 2 stars in the middle merged, and there's another star somewhere thrown into the mix. It's a very complicated, very kind of unusual system. But again, this is an image which has got multiple wavelengths plotted over it. So the blue kind of haze on here is kind of showing the hotter kind of shocked ejector moving out. Then we've got kind of like the dusty emission around it, and then a lot of just things. I think it's visible light in the middle, but a lot goes into making these images. But people go back and look at Eta Carina a lot because it's so interesting, and you can actually see it expanding. So this again is Hubble imaging taken across different years, and you can see how it changes. It's still moving, and you can use these observations to work out how quickly it's moving and trace back the, where each kind of clump was at a given time and how it's kind of evolved. So some regions are expanding quicker than other regions. Some are moving slower, and people are really trying to figure out, what happened with this system, because there is truly nothing else quite like this one. So it's hugely unstable towards the end of a massive star's life, and it happens on such a short timescale. It's really difficult to know what's going on. Okay, so we are truly on the way to a star ending its life now, and each phase gets progressively quicker and quicker. So this shows the structure of the core of an evolved massive star. So it kind of ends up being like a bit of an onion-like type layer, because you've had hydrogen burning to helium, which is a process that takes maybe around 10 million years for a massive star. Eventually the helium begins to, the hydrogen depletes, and you fuse helium into carbon. That might take a few 100,000 years. You then deplete your carbon, for example. You end up with oxygen fusing to silicon. This now only takes about 6 months, so you can see it's getting quicker and quicker as each phase comes about. And then at some point, you fuse silicon into iron in the core, and this process only takes 1 day. And at this point, when you fused all that silicon and you have an iron core at the center of the star, well, you can't fuse iron, because if you did, it would be an endothermic reaction, so it would take energy rather than emitting it. So basically, the power source of the star has stopped completely. So the star now has nothing supporting it from the middle. So all this time it's had fusing in the core, supporting it, giving it energy, giving it life, and then that all of a sudden turns off in 1 day. So then at this point, we move to supernova. So the star doesn't have its power source. There's nothing holding it up against gravity. So basically a star's life is a struggle between the pressure of the fusing in the core pushing out and gravity pushing in. So if you suddenly turn off all of the kind of outward pressure from the fusion in the core, gravity is the dominant force. And this means that the outer layers of the star come crashing down onto the core of the star. And you end up with a supernova. but I'm going to show you a better animation than that one. So here is an artist impression of what's going on when a star goes supernova. So an observer will see a very bright flash as the light escapes from the dying star. The star has lived for a few million years at this point, but this only takes a few seconds. The outer layers will crash down onto the core. I think it's like a quarter of the speed of light. And this kind of shock from the material bouncing off the core. So there's a shock from the material bouncing off the core, and then the supernova expands and travels away. But we've been observing supernova and stars exploding for a long time, long before Hubble. We've probably been doing it for thousands of years. So on the left is some rock drawings from Kashmir, India, 4000 BC. And you can see in the image that there are two suns, maybe. So maybe that was a supernova. We do know that supernovae can light up the sky. So there was a very well-documented supernova in 1054. And this was documented by astronomers around the world, but Chinese astronomers took particularly good notes of what was going on with this. So they said that for a time, a guest star had appeared, and it was there, I think, for a month or so. So they called it a guest star, but it was actually a supernova just lighting up the sky because it was pretty nearby. So it was so bright even that you could see it in the daytime. So on this image, you can just see it compared to, for example, the moon and some other bright objects. And if we look back at, supernova 1054 now, this is what we see. So it's now a supernova remnant known as the Crab Nebula. You would never, maybe looking at it, guess that it was a star that had exploded, but that is exactly what it is. So the star has exploded, and they don't explode very symmetrically like you might see in models and stuff. They explode in all kinds of crazy directions, throwing off material everywhere. And they leave behind these very beautiful looking nebulae, which are full of enriched material. And so that is supernova 1054 today, a particularly nice supernova remnant that a lot of people look at. And again, we're looking at things across multiple wavelengths here. So another more recent supernova that went off, unfortunately, just before Hubble, was supernova 1987A. So this is a star that exploded in the Large Magellanic Cloud, which is a nearby satellite galaxy of the Milky Way. It's one of the, well, I think it is the most nearby supernova that's gone off in recent times. So that's it before, and this is it after it exploded. So you can see the light from this star really dominates the image. It's so much brighter than it was. Like if you look before, that you couldn't even really see the progenitor star in this. You couldn't even see the star that was there before. And all of a sudden, there is this very dramatic explosion. And that is the supernova. But we can get better images of this now. And it is still near enough that, it is near enough that we can get great images with Hubble. So this is what supernova 1987A looks like now. So it's another supernova remnant. This time it looks quite different to the Crab Nebula. So you can see these kind of two rings surrounding the supernova remnant. It's a very weird object. So as astronomers, what we like to do is we like to put things in boxes, and we have a whole system of supernova classifications, type 2s, type 1s, etc. But anytime it doesn't quite fit, we just call it a peculiar supernova. So this is a type 2 peculiar. It's its own thing. But it's nearby enough that we can really resolve the remnant. And some people have spent their entire careers just looking at this object. And you can see the kind of double ring structure there. It's kind of suggested that maybe this was another multiple star system. So there was two stars perhaps involved in some kind of interaction before the system exploded. Okay. And again, yeah, so as I said, if you look at remnants in different wavelengths, you can pick up different information. So this is called the Ring Nebula, and that image in the middle is 3 different wavelengths put together. So if you look with visible light with Hubble, you're kind of tracing elements like oxygen or like kind of warmish material. If you look in X-rays, with Chandra, another space telescope, you can see really, really hot, shocked material that the supernova has like traveled through and heated up a lot. And then if you look with like millimeter observations with ground-based observatories like ALMA, you can see a lot of cool material, so dust and things like this. So these observatories all really work together to bring us these images. So this is the Crab Nebula again, just showing how those layers are built up. So these are all from, I think mostly from NASA observatories. So we've got the infrared, the optical, ultraviolet, those are all probably from Hubble. And then we've got X-ray from Chandra, and again, radio from a ground-based radio observatory. But you can see a whole load of structure that if you only had one of these wave bands, you just wouldn't learn quite as much about the object. But generally, supernovae we see aren't that near, so we're not always that lucky. Usually they're a bit further away. We see them in external galaxies. So I'm going to flash up a supernova now, and you can tell me if you can spot it. Did you see it? No? Okay, let's try again. Yeah, there it is. So it's kind of difficult to see with your eyes, but you know, kind of unbelievably, a lot of amateurs will just look every night and spot supernovae before we do. Like we have surveys looking for them, but some people can just see them immediately. That's not me, unfortunately. But there is the supernova that went off in nearby galaxy M51. And another good thing about the Hubble telescope is now when a supernova goes off like that, there's already been a lot of images taken of that galaxy probably, so we can go back and directly identify the star that was there before the explosion. So it's hard to see in this image, but the star that exploded in 2017 here was imaged in 2007, so we can directly link the star to the supernova. And here's another nice example of this. So the two images on the left and right aren't from HST, but they show the point nicely. So we have a supernova going off in the middle. We can go back through the archival images and spot the progenitor, and then we can wait, if we're very patient, for the supernova to fade away and go back and check that the star has actually gone. So Hubble has been really useful just for this kind of study because there are now so many images from it. And just to bring it back to Betelgeuse, if Betelgeuse were to explode, our nearest red supergiant neighbor, it would probably be almost as bright as a full moon for around 100 days or so. That was kind of a fun simulation that some people in California did. So we would definitely see it if Betelgeuse exploded. But we can also use HST to look at supernovae after the explosion. So I'm just going to play this video. So the same way that when I'm talking in this room, you can hear my voice echo off the walls, light also echoes in that way when it hits new objects. So in here, you're going to see a supernova, and you can see the ripple outwards. That is what's called a light echo. And basically, it's the shock of the supernova continuing to travel, hitting different bits of material along the way, and it lights them up as it goes. So we can study those light echoes to learn about the supernova by kind of like winding back on it. And these supernova are super, super important because it is from exploding massive stars that we end up creating a lot of the heavy elements that we see and need in our universe. So everything on here that has the kind of green color on it is an element that can only be made in the quantities we see it in by the deaths of massive stars. So there's aluminium, there's oxygen, iron, neon. It's really a lot of very fundamental elements. So massive stars are very crucial for the universe and for life. You know, they make the gold, that we have on our jewelry. They make all the calcium in our bones. So they make everything that makes a dog possible. And so these supernova explode, they enrich the environment, and they allow everything that we need for life on Earth to be possible. And that was until kind of recently where we thought the story ended for massive stars, but in recent years, it's kind of got a bit more complicated. So one final option for what happens to massive stars is that maybe they don't explode at all. So this is an image of a red supergiant that is about 25 solar masses. So one that we would expect to go supernova. And this is a Hubble image from 2007. And you can see if we look back in the 2015 image, it looks quite a bit different. So that star has completely faded. It didn't have a crazy bright outburst. It didn't go supernova. It appeared to just blink out of existence in the Hubble images. So it's very weird. And this got people very excited because people love coming up with new ways to make black holes. And one of the reasons is with LIGO Virgo now taking data and detecting things, we keep finding stuff we didn't expect to find. So we need to come up with new kind of pathways for how black holes of certain masses form. And one of these ideas is that maybe some of the more massive stars actually just collapse to form a black hole with little or no visible explosion at all. So that is a very popular theory for what is happening to some of these stars. But as I mentioned before, you can obscure a star quite dramatically with dust. So you can completely change it or block it out completely. And I've already shown you that some red supergiants can be very, very dusty. They can look very weird. Maybe they can enshroud themselves in enough stuff that they could hide from the Hubble telescope. But unfortunately, Hubble's detectors don't go red enough for us to check this. We actually need the James Webb Space Telescope, which is the latest space telescope to go up to check. And for that disappearing star, I was lucky enough to get some data from it a few years ago. And we looked back at the site of that disappearing star. And what we found was a very bright, very red object at that point. So it's still unclear. It is still fainter than what it was previously, but there is definitely a source still remaining at the site of that disappearing star. And we are luckily getting more data soon, so hopefully we'll figure out what has happened to this very weird object. So a lot of people kind of wonder, with James Webb going up, then why is Hubble still going? But they really tap into very different regions of the electromagnetic spectrum. So Hubble kind of nicely goes across ultraviolet, visible light, and a little bit of infrared, whereas the James Webb Space Telescope really covers into that far infrared. So it's really picking up the very cool material, very cool far extended dust that Hubble just cannot pick up. But they work extremely well together. So, observations from James Webb are so often very complemented by Hubble telescope data. So they work really, really well together. Okay, so even after 35 years, Hubble is still one of the most used telescopes by professional astronomers every single year. So every single year, 1,000 proposals are written to get time on the telescope to look at different objects. The chance of having your proposal accepted is around 1 in 5. Sometimes it can be around 1 in 10. It can be even more competitive than this. But there have been over 21,000 peer-reviewed papers using Hubble Space Telescope data. And together, these papers have been cited over 1.2 million times. So the impact that Hubble has had on astronomy is truly amazing. And the one that I found surprising was that 25,000 professional astronomers have used Hubble, which was surprising because I didn't know there was that many astronomers in the world, but there you go. So we're all really hoping for a few more years out of Hubble at least. It's already done so well, but hopefully a few more years of Hubble to top off this 35, maybe 40 would be great. Thank you.
Do you have any questions?
Saw on the kind of chart that showed the life of a massive star, there were several other options, and one of them was that some of the material got recycled, but there was also some about neutron stars,
Yeah.
pulsars, and how would those form?
That's a great question. So I didn't go into that here because it's super complicated, but most of these massive stars that explode, we expect them to leave behind a neutron star or a black hole. but it depends on like very, very specific physics. But in theory, all of these stars should leave behind either a neutron star or a black hole, but we don't even really know which one is going to be left behind by each mass yet. So we're still figuring that out.
Question over there.
You said that red giants were formed when stars burnt all their hydrogen.
Yeah.
What would happen if a star were to burn all their helium before they burnt their hydrogen?
Well, they can't do that because the helium is only formed when the hydrogen fuses together. So if you get two hydrogen atoms and you smash them together, you end up with a helium atom. So it can't do that because the helium burning is what makes the hydrogen burning is what makes the helium. It's a great question.
When a star dies, is it actually very random what it will look like afterwards, or is there a way of predicting what it will look like afterwards?
It seems to be more random than we expect. So I think a lot of simulations that we have assume very, very simple explosions. So they're just going to explode as like a moving out sphere. But actually what we see is that all of these remnants kind of look different. They all have different shapes. They're all kind of different geometries. They all have different things in them. So it's probably a lot more complicated than we think. And at the moment, we don't know how to predict that.
Lucinda's got some questions. Oh, you go.
You sort of talked about how like dust plays a really big role in how like we view. I'm not sure if it was like the supergiant spectra
Mm-hmm.
of a star and like the different wavelengths that are like sort of emitted by it. Like how can you like sort of filter that out? Like do you just shift the wavelengths like away from the infrared region or like?
Yeah, so if we look with different wavelengths, so different infrared wavelengths can tell us how much dust is somewhere, or you can kind of see through it looking at with the certain wavelengths, and then we can take a star that we know what it should look like. If we have like a very simple star, we can say it should look like this, and then we can work out how much the dust is affecting that star, and then we can kind of correct everything else around it. But it's quite fiddly, and you have to be sure that you know what you're looking at, and that's somewhere that people make a lot of mistakes. It's very difficult.
Thank you. I think with the wealth of image that has been captured in the past few decades, I don't know if there has been any research that is using AI to analyze anything in this topic, and if I guess there must have been, and if there is, like, what are the surprising things that AI has helped?
Yeah, so AI is really going to be hugely important in the next kind of era of this field, because there's a new survey that's going to be start happening called the LSST survey. So it's going to be detecting like thousands of kind of explosive events every night. And what we're going to do is we're going to use AI to filter out what's interesting, what's worth following up. So there's a lot of people working on that at the minute. That AI can also be used to kind of spot things that change in brightness from like archival images as well. So loads of people are working on that, and hopefully it will just make everything like a lot quicker.
Lucinda has some questions online, and then I'll come back to you two with your second questions. Okay.
There's about 8 questions on the line. I'll try to get to them quickly. One that we have a guest on YouTube who is asking about type 1A supernova. Wondering if we will find out how the James Webb Telescope can find these if necessary, and if so, should Hubble Space Telescope finish everything on where we started from?
Well, James Webb is already finding 1A supernovae. We find a lot of them. They're quite common. They come from lower mass stars, probably from binary stars interacting and things like this. But Hubble looks for them. James Webb looks for them. Yeah.
So kind of coming up back on the cosmic dust, that Kevin's wondering, what is cosmic dust made out of?
So it's basically everything that it depends where in space you are. If you're in like a young cluster where supernova have happened, then it's enriched and it will have some of these heavy elements in. But if you're in the early universe, the dust will be just cold hydrogen and things like this. And you can kind of think of it not like dust like we have like here. It's more kind of like a very fine like cigarette smoke kind of veil of material that gets in the way. It's very, very, very fine.
Sumit asks, what happens to all the energy released from birth and the death of stars? How accurate are our measurements or observations?
The energy is put back into the surrounding medium. So it's put back in by, shaping these nebulae or shaping these clusters, blasting material out. So the energy is put back in, and it is something that's tricky to measure, but there are quite a lot of different ways to do that. So you can measure like velocities of like outflows and things like this, and you can kind of work out from how bright something was, how energetic it was. So there are ways of doing that.
This question is really interesting because I was curious about AI as well.
Uh-huh.
Can we tell when a star is about to go supernova? But Nigel asks, how do you detect which nuclear phase a star is in? And can you detect when a star is in the iron stage and hence about to go imminent supernova, and then direct observations to view the event?
Basically, no. You can't see that. The closest you can see is looking at red supergiants. You can maybe say which ones are more evolved, but you would still be guessing to within like 10,000 years if it's going to go or not. It's like super, super hard to say when a star is very close. There are people looking for precursor emissions. So some people think that maybe these stars that explode have a little flare before they explode, and some people are trying to detect that in the days before a supernova, but it's very difficult. The sky is really big.
Okay, you eat one more question.
Okay.
I was wondering, I remember you showed a picture of a red giant that would be massive compared to our sun.
Yep.
So how would that? I think I heard it would engulf the Earth. How many more planets would it engulf?
So a red giant would, yes, when the sun eventually becomes a red giant, it will engulf the Earth, probably maybe get, I don't know, I'd be guessing whether it might get to beyond Mars. It would expand quite a lot.
After the few years that the Hubble Space Telescope has left, will they put up a new telescope that can also take ultraviolet pictures, since it's that complementary?
Yeah, so there are a few projects looking at doing that. So there's one called Ultrasat, which will probably go up in the next year or so. I think that's happening. And that does, I think it's only got a short lifetime, but basically, yeah, people are working on that because the UV is a very important region to get information on.
And a question from this gentleman over here. So if you
Do you think there are any exoplanets in the orbit of any red giants or massive stars that are potentially habitable? With the shortened longevity of massive stars, maybe not, but I'm not quite sure.
Yeah, that's a really good question. Around red giants, we do find exoplanets, but I don't know how habitable they are. But around a massive star, it would be really, really difficult to get an inhabitable planet in the lifetime that these massive stars exist for. It might just be too quick for that to happen.
I have a question about your career path, wondering what was it that inspired you to choose this area of astronomy to choose? Why did you choose red supergiants?
I chose it because I thought, oh, things exploding, that's so cool. So I thought that would be really fun. And also it's a field that is changing a lot with all this new data that we have. So it's one of the older fields in astronomy, but now we're getting new data. We're realizing a lot of things are kind of wrong, and I like correcting that.
Then I have an online viewer who asks, what is your favorite star?
My favorite star. I don't know if I have a favorite star, but that cluster Westerland 1 that I showed is pretty cool. There's a lot going on there. It has all kinds of massive stars. It's got red supergiants, Wolf-Rays, luminous blue variables, all like very, very close together, which is super, super unusual. So that's a pretty fun one.
one question there, and then I've got a question.
because we're at 7 o'clock, so.
Thank you. Excellent lecture. Can I ask you about rotation, the spin of a star?
Sure.
Some stars spin very fast even before they collapse.
Right.
And then when they collapse, you can end up with a pulsar spinning 1,000 times a second. So how much influence do you think that would have on the shape of a nebula, not a nebula, but an explosion? How much would that affect the distribution of surface?
Yeah, probably quite a lot. It might affect, let's see. So if something is rotating really fast, it can live longer, which may give it more time to kind of come out with these crazy shapes. It might have a more kind of unusual like dust pattern around it because it's had just more time to build up those kind of layers. And if it's rotating as well, it's had more time to interact with anything nearby. But massive stars don't rotate crazy fast, we don't think. But it probably would affect it. It would just mean they live longer and have more time to get weird, I guess.
In the space technology, whatever the informations we are getting through the electromagnetic waves, which we are giving us the information and getting about the space, is there any project is going on which is beyond this? Can we discover something, or any project is beyond the electromagnetic waves? Whatever the information which we are getting today is because of the spectrum, what I have mentioned, and light. Is there anything which is beyond that, which is not known to us?
I mean, that's a great question. So going beyond the electromagnetic spectrum is something that we're trying to do with gravitational wave surveys. So rather than looking at anything in the electromagnetic spectrum, we're looking for these ripples in space-time that we can use to, find out information about neutron stars, black holes, in a way that we just can't with this kind of light. We just can't see black holes. Neutron stars are really hard to detect. And we're finding out a lot of things with gravitational waves that we can not do with electromagnetic light.
With your career, and like, do you also look at explosions and supernovas at the quantum level, or
At the what level, sorry?
quantum level, like with like?
Oh, I don't do that.
Okay.
No, I wasn't very good at quantum physics in uni.
One last very quick question. You spoke about Betelgeuse.
Yep.
If at this exact moment it were to go supernova, how long before the light would reach us?
How far away is Betelgeuse? Try to think how far away it is. I think maybe a few years, 4 years or so, something like this. Yeah, it wouldn't be immediate. It would take a bit.
Well, thank you so much for helping us celebrate 35 years of the Hubble Space Telescope. Please thank our speaker, Dr. Beasor. Thank you for coming to the Royal Astronomical Society.